Okay, so here we are. This is this right here is I guess it's lecture 5 of the class, but we're really a lecture behind. As last class I was ill, and Jin Chang covered the remainder of lecture 3 during what we would have normally had lecture 3 and lecture 4. Now, this is where we left off in lecture 3 on Tuesday of last week with time sample domain operations. We talk about, delaying a signal or moving it. That's not what I expected to do there. Delaying a signal or moving it sort of to the right on the axis, which is this operation. And then advancing a signal, which is sort of shifting it to the left on the axis. And then, of course, there's the the example where we actually have a delta function, which is an example of some signal, and we show how you can actually use just the definition of the function. So this is delta of n, and it's defined this way. This is how it's defined. Now, if we want to find the place where this thing evaluates to 1, we look at the argument and we say, when does the function n equal 0? Well, because that's where, when n is equal to 0, it evaluates to 1. And so I'm pointing out a very trivial concept, but I want to be very clear about it, is that this generalizes. So whatever function is inside here, whenever that function evaluates to 0, the delta function will take on the value of 1. So again, this is the function n minus n0, and when you set that equal to 0, you can find out where this delta function will evaluate to the number 1. And that's for the value of n that is equal to n naught. You just solve for n. And that means at the index n naught, this delta function will occur. So if I were to plot it, I would plot it as a delta function having the value 1 at index n naught, where this is the axis. So theoretically, that's how it would be plotted. Does everyone follow that, or are there any questions about that? Because if that's totally clear, I'm going to ask you a little bit of a brain teaser. The brain teaser is, this is n squared minus 2n plus 1. Where does this delta function take on the value 1?
Zero.
Well,
And
what's our process for solution? How would we figure it out? So I say it's going to be equal to 1 somewhere, and it's going to be equal to 0 elsewhere, but what values of n will it be equal to 1? How would we solve that using the procedure that I just outlined?
Would it be n equals 1, or where it'd be shifted over to?
Right, the procedure would be, let's set the n squared minus 2n plus 1 equal to 0, and find out the values of n that make this equation correct, that satisfy this equation, right? What are the two values of n that factor this? This is n minus 1 times n minus 1. And so, in fact, it takes on the value 1 when n is equal to 1, because if you plug 1 in here, you have 1 squared minus 2 times 1 plus 1, right? And that's equal to 0. So it's correct. But I want you to, what's critical here is this abstract thinking. I have a delta function, and there's something complicated in the argument of it. What I need to do is I need to find the integer value of n, right? N is an integer. That satisfies this equation equal to 0. So if I were, say I were to write this as n squared minus 1, right? A delta of n squared minus 1. What would be the values that that function would be equal to 1?
Positive and negative 1.
Right, n squared minus 1 is n plus 1 times n minus 1, right? Right?
Yes.
Correct.
Yeah, so then this delta function, because the argument has multiple roots at integer values, it's going to be equal to 1 at n is equal to plus and minus 1. All right, so it's not as trivial as you might think, right? And the procedure that I'm showing you is actually a procedure that just works all the time. Was there any questions about compression or expansion? So when a is greater than 1, the signal is compressed or it gets shorter, and so we show a signal here on the right, and then the compressed version of it is shorter and it's losing samples, right? Because you make it shorter and it only takes on values at integer locations. If it becomes shorter, well, you have to throw out values. In this case, it's gone have. This looks like the compression. This situation here is x of y of n is equal to x of 2n, and that has the effect of discarding all of the odd indexed samples. So this sample is gone, this sample is gone, and this sample is gone. And similarly on the positive axis, this sample, that sample, and this sample were deleted. They do not appear in the signal. All of the odd samples. Yeah, the recording is already started. I don't record. Please recall that I don't record through Zoom. I record using this. Yeah, you're all right. You're all right. Thank you for. It's always good. So there have been. I record through OBS. But there have been instances where I've also forgotten to do that. Shamefully, I'm sorry. But this particular instance isn't the case. Although I did do a complete upgrade of my system, moving to a new distribution of Linux. So I'm going to go ahead and verify that the file is actually being created. I see the file there. It is being created. So I think I've double checked it just to be sure. Okay, so when this number is greater than 1, the thing in front of the n, this a, we're doing a compression. When it's less than 1, like it's a fraction, like if you have x of n over 2, right, then a has the value 1/2. Well, then we're stretching things out, and this is exactly what you would see in this circumstance. You stretch things out, and you insert zeros wherever you did not previously have a value. For example, at 0, is this the same value here? This value here goes to here, but we have to insert a 0. So these things are inserted zeros there and further at every one of these odd locations. Okay. If there's no questions about this, then there's no point in belaboring the subject. The timer.
I have a quick question.
Yeah.
So, right there, you said make the odd one 0. When would you do the interlope or interpolated expansion, where you find the average between the two?
So in certain circumstances, we might ask you to fill in those 0 values with some kind of convention. And one convention is, say, linear interpolation. So in linear interpolation, you are basically saying, let me see if I can find a clean part of the slide to write on. I kind of messed things up. Let's go over and use this part over here. So let's consider that we want to interpolate the value of x of y, at the value 7, right? So y of 7 would equal x at 7 over 2, or 3/2, right? So y of 7 in this case would equal x at 7 over 2, but 7 over 2 is not an integer, so we just that value doesn't exist, so we by convention it is 0. That's what you would do without interpolating. But when you are interpolating, what you do is you say that y of 7 is in fact equal to the arithmetic average of its closest neighbors, right? And so in this case it would be 1/2 of x of 6 over 2 plus x of 8 over 2. Now those are both integral values, so that's x of 3 plus x of 4. So it's the arithmetic average of the two values on either side. Does that make sense?
Excuse me, Professor. I can't seem to make out what you're writing in green. It makes sense, but you can't exactly see.
Okay.
I don't know if anyone else has that problem, or
So this
maybe I
is
set
x
some up wrong.
of 6 over 2. This is 8 over 2. So is that clearer?
It's a lot better.
That's clearer.
Yeah, okay. So this is 0.5. So 6 over 2 is 3. So this is x of 3 plus x of 4. So is that okay?
Yeah.
Yes.
Okay, and so that means that we're just taking, so to get this value here, if we wanted to do interpolation, we're taking the average of this value and this value, which correspond to this value and this value from the original signal. X of 3, that's this value, and x of 4, well that's this value here. Now they end up at 6 in y of n in the output signal, and at 8 in the output signal, because that's what time expansion does. We're expanding time by a factor of 2 here. So, this last value, which was at 5, is going to end up at 10. So everything kind of the whole scale of the x-axis or the n-axis is changing on the output. And just to be complete here, and I don't know, hopefully this will show up. It's called linear interpolation because we're connecting a lot. Okay, that should be a line. We're connecting those 2 points with a line, and then we're calculating. The value of our solution here in linear interpolation is entirely equivalent to say taking a straight line. Now we're going to imagine that that's a straight line, and connecting the 2 points, and then taking the location off of that line corresponding to the place where we need the value, the x-axis. So that's why it's called linear interpolation. We are interpolating or finding a value in between two known values by estimating it as coming from the polynomial curve, which is a line. So you might think of sort of a coordinate system defined at this location, where the y-intercept is the value here, and the slope is basically the difference in the values, and we're basically figuring out where on that line the other value lies on the x-axis. Is that clear?
Yeah, that makes it a lot more clear. Thank you.
Yeah. Okay. So any other questions? So about this. Here's the linear interpolation right here, and so it shows an example. And it generalizes, like if we were to do n over 3, well then there's more stretching as a factor of 3, and you're inserting 2 samples, and then it's sort of 2/3 the value on your left for the left sample and 1/3 on the right, and then 2/3 the right sample and 1/3 on the left. So you kind of weight the value you're closer to. So when you're stretching by a factor of 2, they're sort of equally close on either side. So the weighting is half. So that's linear interpolation. We did time reversal, which is just reversing. Everyone on the n-axis goes to the corresponding location on the opposite side of the origin. So this guy goes here, and this guy goes here, and the same for every other value. Sort of a mirror image with respect to the origin along the x-axis or the n-axis. I'm not sure that we want to belabor the point. Did everyone understand the procedure for how to calculate, say, the location of a step function like this? Was there
No, could we go through the example?
So this here is, so let's go ahead and do this example here. And so this is a step function, and one of the fundamental questions students would have is like, when does this function occur and where is it equal to 1? Like if I were asked to plot this. And my recommendation to you is to keep things straightforward and simple, and just use your knowledge of inequalities and the definition of the signal. This signal is defined to be the value 1 whenever this function is greater than or equal to 0. All right, now all we have to do is 2 things. We have to keep in mind that n is an integer, and we have to know how to solve this inequality. So how do we solve this inequality for n? Minus 2n minus 5 is greater than or equal to 0.
Just solve for n.
Well, let's go ahead and how do we go ahead and solve for n is my question. There's one
Do that.
How do we change? I guess there's one trick to this, and the question here is changing the sign of n. Divide by minus 2, which changes the sign, and also
Gets rid of that quality.
what happens to an inequality when you multiply by a negative like that?
You change the sign.
Yeah, you have to flip it.
You flip the inequality, and this is what is very commonly forgotten by students. So let's go ahead and do that operation suggested by Zach. I'm going to multiply by minus 1/2. When I multiply by minus 1/2, I get n plus 5 over 2, and this happens. Right?
Yeah.
Yes, very important. Now I say n is less than or equal to minus 5 over 2. Okay, that is how easy that is. So if I were to plot this, this will be equal to 1 when n is less than or equal to negative 5/2. So if I were to plot this, would the plot start at minus 5/2 or minus 2.5? Should I go out here, go out to minus 2.5 on the n-axis, and then say that it's 1 here?
No, shouldn't it start at an integer value, not a decimal value?
Precisely. Yes, thank you. Exactly. So what is the first integer value, n, that satisfies this inequality?
Negative 3.
Negative 3. These are all... Yes, so you've now deciphered all of the potential complexities that can come up from this. So we know that this is a step function that's going to be 1 whenever n goes on forever this way. And it was that simple. It was that simple. This cannot fail. This is just using math. There's nothing that we've done special here. There's no order of negativity or flipping or translate. You don't have to do anything other than simply look at the inequality and use the ability to solve an inequality to solve this question. And so this also applies for all such questions of this nature. if we use this approach, it will always work. So when I give you techniques for solution, I give you techniques for solution that cannot ever fail and often require the smallest amount of absolute, diversity, like things you have to memorize. There are two things here. Solve the inequality, remember, n is an integer. Any questions on this? So here we talk about representations for signals, and we start to involve this infinite sum situation here. So this is a discrete sum. It goes over k. And in this case, we have a bunch of delta functions. And I want to ask you, where does the delta function n minus k occur? At what value of k, or let's look at it in terms of n. I guess it doesn't even matter. When is delta of n minus k equal to 1?
When n is equal to k and when n does not equal k.
Yeah, it's 0 when n does not equal k, right?
Mm-hmm.
So this delta function occurs when n is equal to k. And so when you start looking at delta functions, it's always kind of have to know where it happens, because this is a function of n, and it's got these other things, and these other things occur at index k. So now they have these graphical representations where they have a's here, and these are different values of n. And so now they're saying, okay, well, you can represent a signal as a sum of delta functions. In this case, delta of n plus 3, where does this delta function occur? When n
At n is equal to -3.
Right?
Yeah,
And
3.
so it has it multiplied by a to the minus 3. So if we look over here on the left-hand side, at the index minus 3, which is this location right here, we have this value a of minus 3. So essentially, we're putting this one value here on the graphical representation corresponds to this single term here in the mathematical representation. So these are two different representations for exactly the same signal. This is the graphical representation. This is the equivalent equation. And so you can see term for term. Well, here's a term a1 that occurs at n equal to 1. So I take a1 and I make it only occur at time index 1. I can do that by multiplying a1 by this delta of n minus 1. That's going to restrict the value of a1 to only occur at index n equals 1. And so we can write out any signal as an infinite sum of delta functions where the value of the signal for each index of n is taken as the coefficient, say, and the index of the index where that value occurs is taken as sort of the delay value of the delta function. So a2 occurs at n equals 2. So n minus the minus 2 here is the location on the axis. So similarly, the delta function is the integral of the delta function is the step function. So if you go ahead and integrate in this direction, well, the delta function occurs at 1, so you get zeros all the way up until you get to the location of the delta function, and then after that you count the value of the delta function, which is 1, but then there's no value after it, so it just remains constant. There's no other values to accumulate. So as such, this u of n is the integral of delta of k, so it's the integral from minus infinity to n of delta of k. So this is the integral relationship between the step function and the delta function. So you can write a step function as a sum of delta functions. Similarly, you can write out all of the different terms this way. So we talked about exponential sequences quite a bit, so I'm not sure that I need to talk about this, but we can also combine sequences. So if you have the exponential function, you multiply it by a step function. The step function serves to restrict the values, restricts the locations of non-zero values. And in this case, just multiplying by the step function here just makes it so that the function is 0 in this domain, and then it has the behavior of a alpha to the n in this domain, right? All right, and then they went over power and average power, energy, power, and boundedness. So those are signal attributes. So unless there's questions about them, I'm just going to go into the next lecture from here. Okay, so that's done doing that. Let's start on lecture 4 here. And by the way, I will be publishing the next homework too shortly, so you should see that as available to you for the next week. Okay. So this is discrete time system properties, kind of a reviewer of your system properties that you discussed a little bit in 2254 and yet again in 3111. This is your last experience with system properties. Of course, the biggest and the most important property that we need to be masters of understanding is the linear and time invariant property. So we will be seeing those properties again. So, discrete time system, you can represent it mathematically as a transformation of values. So you have input values, there's some operator t that operates on the input values in some mathematical way and then generates the output values. So this is a representation, mathematical representation for a system where t is a mathematical operator. For example, what is one very specific mathematical operation? A linear operation is the integral operation. So t might be an integrator, right? Like what we saw on the relationship of like u of n is the sum from k equals minus infinity to n and delta of k. Well, sort of a lot of stuff going on here, but you might say that this is a system with the input. So x of n is equal to delta of n. So in that case, this is the input. And then the output would be so we'd say that the output here is the step function. And what is the system itself? The system is the thing operating on the input. It's the integrator. So systems themselves kind of don't. We define them. They have to operate on something in order to generate. They need an input to generate an output, right? If you have an integral sign, somebody needs to be a subject to that integral, like x dx. That's the input, and what comes out is x squared over 2 plus c, right? And that's the indefinite integral of x, right? So the integral is an operator. It operates on functions, and when it does its operation, new functions come out. So that's how systems are defined. Here's an input. It's some signal. It's a function. T is a thing that operates on the signal, and then a new function comes out. So this is how systems are defined. Here's an example of a system. This is a moving average system, and this might look like a lot of equations, but it's actually not to be worried about too much. First of all, we presume that m1 and m2, both of these are positive numbers. They're greater than 0. Okay, and so if we start thinking about that, let's say that m1 and m2 are equal to the value 1. Well, then what does this thing really boil down to? It comes out to be something like k goes from minus 1 to 1, x of n minus k, and then there's a constant out in front that I'm going to write later, but it's 1 over 1 plus 1 plus 1, right? Or 1 over 3, right? So this ends up being 1/3 x of n minus 1 plus x of n plus x of n plus 1. and that's what it would be for these values. That's just a three-way average where all the values of x, the next one would be, the next value of x would be x of n plus 1. Let's say that we have n equal to 0. What does this look like? You have 1/3 x of minus 1 plus x of 0 plus x of 1. And so you can see that what it's doing is taking the function values at three neighboring locations. The current location, in this case, is 0. The previous location, which is x of minus 1, and the next location, which is x of 1. And it's taking their arithmetic average, 1/3 of the sum of their values. So this is a moving average because when n changes, the various values change. So if n were equal to 1, I wouldn't be considering minus 1, 0, and 1. I'd be considering 0, 1, and 2. So the average moves with the index. So I point out another example where I have set m1 to 0 and m2 to 3. And that's a collection of 4 values. The current value, so to speak, at index n, and then the previous 3 values, the prior one, the one that's 2 previous, and the one that's 3 previous. And then I take 1/4 of their sum. So, you might think that this would be a relatively simple thing, but I can tell you that things like this are actually used very much in practice for, say, denoting trends in the stock market. The moving average for, say, the Dow Jones Industrial Average or any stock, whether Amazon or Google or whatever your favorite stock is. And so the moving average is some kind of an indication of stability, whether the moving average is changing significantly. This is, yes, as someone, Austin mentioned, is this a low-pass digital filter? Yes, it is. Because if every one of these values is changing rapidly, what you'll find is that the signal that you get by averaging does not change as rapidly. We will always have less variation than the signal that comes in, meaning that the higher frequencies, the frequencies in that signal responsible for those variations have been eliminated or attenuated, which is what filtering does. But anyways, we don't want to get too much into the frequency domain concepts of filtering quite yet. But it's always good to, discuss them in place so that when we do come to that theory, they're easily relatable back to previous lecture content. Any questions about the moving average? Now, the bigger you make these values, say you make m2 equal to not 3 but 30, then you'd have 31 values over which you're averaging, and it's a much larger interval in time, and it would involve 31 different signal values instead of only 4. If there are no questions, I'll go on. Okay, examples of discrete systems. Well, you can define any system, anything that takes input values and makes output values, is a discrete time. As long as the input is discrete and the output is discrete, so defined at integer values, then it can be represented as a discrete system. So here I take a max value. In this case, the system is actually the max operator that's operating on 3 input values, and it's taking the max of these 3 specific values. You could also just as easily say that the output at time n is the max of other values, or the min, or those are all valid discrete systems. In this case, it takes the current index, the previous index, and the value of the function that's previous to that, and sees which one of them is maximum, and then it outputs that value. So this is used a lot in image processing. In fact, this is used extremely frequently in artificial intelligence. They call it max pooling. They take a bunch of values they summarize all of those values using only the maximum value of all the values. It's called a max pool operation. That's intrinsic to a lot of artificially intelligent systems in their internal workings. Here's another system. This is the ideal delay system, and it's just the output is just the input, shifted in time. But in this case, it would be shifted to the right by n naught samples. But if n naught were in fact a negative number, then it would be shifted to the left by n naught samples. Okay. The most critical property of all the properties is this linearity and time invariance. These are the most we use and reuse those properties the most. So this slide talks about the linearity property. Linearity is actually a combination of two properties. There's this idea of additivity, right? So a system is linear, and we need to keep these thought experiments in mind, because I will ask you if a system is linear, and in order to understand whether a system is linear or not, we need to make a thought experiment. All right, the thought experiment for additivity is this. We take a signal x1 and we put it into the system, and we get this output y1. And then we take another signal x2, we put it into the system, and we get another output y2. All right, now the system is linear if and only if we can take the addition of those two signals, right? We have x1 of n and x2 of n, and we input that to the system, t, and what comes out, we're going to call that y3 of n. Now, if the system is additive, y3 of n is going to equal y1 of n plus y2 of n. Alright, now that's just a bunch of math and algebra, and it's all really trivial and it sounds almost meaningless, right? So here we have x1 goes in, gives y1, x2 goes in, gives y2, then I put x1 plus x2 in and I get y3. We're going to do an example where we show this in practice, and show that it actually does work in some cases, and for other systems it doesn't. And so the homogeneity or the scaling property means that if I take the signal x and I scale it by some factor a, and I put that into the system, it's equivalent to take x, put it into the system, get an output, and then multiply the output by a. That's the second property for linearity, which is the scaling property. Now if we put both of these properties together, that means that we can take x1, multiply it by some scale factor a, put it into a system, get out x1 times a output. Take b, multiply it by another signal, x2, and put that into a system and get x2 times b as output. Or we could take their entire sum, a plus b, and get this as its output. So this tests both properties for both signals at the same time. And it's the most developed and complete description of the linearity process, or the linearity property. So I'm going to give a demonstration of how to look at how to apply this idea, but is there any questions about the specifics of the slide or the idea itself?
Yeah, I have a quick question, Dr. Willis. Whenever we're doing this proof, the mathematical operator needs to be the same, right?
Yeah, this is a system property. So this is a system, and this system here is always the same system.
Right. Okay.
Right, and so where the question is posed like this: for this system, is it linear? And the answer is either yes, it is linear, or no, it is not. It is only linear if for all possible x1 and x2, and for all possible scale factors a and b, this principle of superposition, which merges both of the properties, is true. And then I'll demonstrate how we answer that question. So here's here's a actual example. So remember, this is the conceptual diagram. We do a thought experiment, and it involves generating 3 signals. The first signal is just I put some signal x1 in, I get some signal y1 out. I put some signal x2 in, I get some signal y2 out, and then I put some signal generated from the first 2 signals I assumed to begin with, x1 plus x2, and I generate a third signal. And I ask the question, does that third signal equal the sum of the other 2? If it's yes, the system is additive. And usually, and then I also can put an A and a B here, and an A and a B there, and then ask whether it's scaling too. So this is the additivity property. Okay, so here's a system. Y is equal to xn squared. And what I'm going to ask is what this is a linear system. So first of all, any input-output relationship is a system. If y of n is here, and I make it equal to some equation where x of n is on the other side, that is a system. So this, in fact, is a representation for a system, just an equation involving x and y. It's an input-output. So what is the system? Well, in this case, the system seems to be taking the values of n and picking off values of x where n is squared and setting them y at index n to the value of the function of x at where it's squared. But let's go ahead and apply our process. So we look at, this is our thought experiment. We do these 3 lines here. That's step 1, step 2, and step 3. That's step 1 in practice, step 2 in practice, and step 3. I take x1, I put it into the system, I get y1. That gives me an example of what the system does for x1. I take x2, some signal x2, I put it into the system, it gives me an example of what it comes out. Then I add the 2 things, and I get an example of y3. So then I ask myself, is y1 plus y2 equal to y3? And the answer is yes, this system is additive. In general, we're only modifying the sample domain, the index domain. So how it behaves on the values of the function, which is how linearity looks at it, it's not a problem at all. Any questions on that example? Here's an example where we show it's not linear. So we have this system, y of n is equal to the sine of x of n. So the system here, the t in this case, is equal to the sine function, right? And so x of n is going in, and then the sine is taken of the value of x of n, and it generates a new value, y of n. So if we were to look at it like a block diagram, that's kind of how it looks. When we write it as an equation, it looks like this. So let's do our steps. So step 1, let's say that x1 goes into the system and y1 comes out. This is what we get as an equation. Step 2, let's assume that we put some signal x2 into the system and y2 comes out. That's this here. Okay, well, let's step 3, as I take the sum of x1 and x2 and I put that into the system. Well, remember, the system here is sine, right? So x1 plus x2 gets added and goes in. This is the place where most students run into a problem. They forget. It's not just the addition of these two, it's what the addition of x1 and x2 all go into the argument of the sign. And so this is step 3. And so we've done the 3 steps correctly here. And now we have to ask ourselves, is y1 plus y2 equal to y3? So that's equivalent to saying if the sine of some value a plus the sine of some other value b is equal to the sine of the 2 values summed, sine of a plus b, right? Because these are just x1 and x2, they're just numbers, right? x1 of n is a value of a function at index n. x2 of n is just the value of a function at index n. So to simplify the thought process, I'm just going to write down the actual question at hand here, which is this. Is this relationship true for all values of a and b?
Repeat the question again.
So is this relationship here true for all values of a and b? Sine of a plus sine of b is equal to the sine of a plus
No.
b?
No.
I don't think so.
That's correct. It's true for almost no values of a and b. Let's take the sine of pi over 2 plus the sine of pi over 2 is equal to the sine of pi. Is that true?
No.
Right. Yeah. So if you took any value, there are values that make this work. But it has to be true for all values. This is only true for a microscopic number of values. So it is certainly not true for all for all values x1 and x2. So this is not linear, and the system is not additive. If it's not additive, it's not linear because it has to be both additive and scale. Any questions on this?
Yeah, so Dr. Willis, so whenever we're writing if we're using slide 6 as the backbone for the derivation here to check, whenever we write T operator, it'll be T operator A x1 plus B x2 is equal to, and then distribute that, right?
Yeah. So
So
you
if
can
I'm
think
trying
of
to
this,
use
you can
this
think of this.
to-
This is y3,
Right.
And this is y1,
Right.
and this is y2.
Right. So how will we use this idea, this right here with that sign function? I'm kind of confused.
Okay, so this one is y1, this one is y2, and this one is y3. So
Right.
in this case, this would equal sine of x1 of n. I don't know, maybe this isn't y3 is equal to sine of x1 of n plus x2 of n, right? This was this here is y1, so this term here is sine of x1 of n, right?
Mm-hmm.
Because remember, this is y1 is sine of x1 of n, y2 is sine of x2 of n, and y3 is sine of x1 plus x2. So this is y2 is sine of x2 of n, right? And so then this has to be true for it to be, the principle of superposition has to be obeyed for a linear system. But this is not a true relationship, so this is not satisfied. This is not linear. The
Right.
system that is the sine, this system, sine of the input, is not linear.
So for any sinusoidal, whenever we're testing, make sure that we put the signals into the operator. I mean, into the
Yeah, fundamentally,
argument,
you have
right?
you have to identify what the system is doing. In this case, it's the sine function, and the fundamental question is whether or not the function, the operation that's going on in there is distributive, right? If t of a plus b is equal to t of a plus t plus b, that's a distributive property, right?
right.
And so this additivity thing, you can kind of ask yourself, is this thing, this operation that's going on here, distributive? Is it distributive? If it is a distributive operation, then you have a linear system.
Gotcha.
Does
So
that
what
make
about if we had like a complex exponential? Then we would have to put
Well,
x1 and
well, we can
x2
just
into
go
the
ahead
argument
and-
of the
Do we
exponential.
have well, why don't, there's no, I guess nothing's telling us we can't do that. What if we have the system e, so I'll write down y of n is equal to e of x of n, and now we have it. Okay, so what's y1 of n? It's equal to e of x1 of n, right?
Mm-hmm.
y2 of n, that's e of x2 of n. And then y3 of n, Well, we have to add the inputs and then put it into the system, which exponentiates. So it ends up being e of x1 of n plus x2 of n. And then,
Okay.
and so in this case, is this a linear system? Is e of x1 plus e of x2 equal to e of x1 plus x2?
Yes, actually.
Careful.
Oh no, it's not. No,
This
no,
is
it's
a
not.
plus here,
You're
not a
right.
multiply,
Right.
right? So the answer,
Yeah, I was thinking of multiplication
yeah,
there.
no, this is a plus, not a multiply. So
Right,
because
right.
it's a plus, this is not a linear system. So exponentiate the system which exponentiates the input, in fact, is not a linear system. Is that clear?
Yes, yes, that makes a lot of sense. Thank you.
Yeah, thanks. So linearity proofs. So again, the approach for solution is apply the diagram and test for equality. So here's a summation. Like we're doing an integral, right? You surmise that integration is linear because I already told you that. But it's also all of our differential calculus is linear. So differentiation is linear, integration is linear, all of that stuff, and that's what's said here on the slide. But let's go ahead and apply it. Guess what? This one here, this is y1. y1 of n would equal the sum of x1 of k, and that's what comes out there. y2, so this is y1 of n. This here is y2 of n. And this here is y3 of n. And so in this case, the sum is distributive. You can take the sum of x1 plus x2 and distribute out the summation operator like this. And those are equivalent sums. So the summation operator, or integration more generally, is distributive. This is the term for continuous integration. And is differentiation distributive? Yeah, if you take the derivative of x1, you get this. If you take the derivative of x2, you get this. If you take the derivative of the sum of x1 and x2, it is equal to the sum of the derivatives. Is the derivative of the sum equal to the sum of the derivatives? Yes. And in fact, much of superposition or the additivity property is saying for some operator, is the operator applied to individual pieces equal to the operator applied to the sum? Like in the previous slide, we asked, is the sign of A plus the sign of B equal to the sign of A plus B? So is the sign of two numbers equal to the sign of their sum? Is the exponentiation of two numbers equal to the exponent of the sum? It's always the same question. So after we do a few of these things, we find out that there's a pattern here, and just being familiar with that pattern and knowing how to apply it is what you need to be able to solve these questions without error. So here's another linearity proof. We're asking, here's a system that does an ideal delay, and so we apply the idea and we get the full idea where we get this is y1, this is y2, and if we apply it to the sum, we get this y1 plus y2, and we find that for the scale factor a, of course it doesn't seem like the scale factor here is included, but if you put an a in front of this and an a in front of that, you have equality. So this is in fact a linear system, just the same process. Oh, look at this, we even have your exponentiation example. We've already done it, so there's no need to redo it. But we could do this one here. X at y of n is x of n squared. Okay, so what's the system doing here? It's squaring the input at the given value. Well, let's see what we get. y1 of n is equal to x1 of n squared. Sorry, it's supposed to be a parentheses. y2 of n is equal to x2 of n squared, and then we need to put two values in and then take the square of that. So y3 is going to be x1 plus x2, and then the system operates on it by squaring it. And then we ask ourselves, is y3 equal to y1 plus y2?
Yes.
Hold on a second here.
I think.
Right, we multiply this guy out, and we'll get x1
Oh yes.
squared
Oh, the basics.
plus 2x1 x2 plus x2 is n squared. So don't be so fast. You have to kind of make sure you look at all of the terms. This particular square has some hidden terms in it. Namely, this term here exists that doesn't exist in the sum of these two guys. So this plus this is not equal to this. So this is this here is not linear. And it's kind of like we would ask ourselves the question: is the sum of two numbers squared? Is a squared plus b squared? Is that equal to a plus b squared? That's kind of what this question is asking. And in general, for values a and b that are arbitrary, this certainly is not true. We've already solved this. We know that this is not linear, so I'm not going to solve it again here. Any questions? Okay. Time invariance. So time invariance is this idea that a system will behave the same way regardless of when input is applied. All right, so I am to the best of my ability a time invariant system. So you might end up hearing that before the end of the semester, because sometimes students ask me, you know, to say extend the homework, and I say no, and then they ask me again. And regardless of the time that the input is applied, I have the same output. You know, it's shifted in time. So, but in this case, it's the same. But so the idea of time invariance is that the system is going to behave the same way, no matter when the input is applied, right? It doesn't mean that the system will always behave the same way. It just means that if you go and interact with the system on Friday, and say you interact with the system again on Monday, if you give it the same input, it will give you the same output. And we like time invariant systems. It allows us to be able to predict what will happen in general. So I always use at this point in lecture, I usually use the podium, the lecture podium, as an example of a time varying system. Because every day that you go to the podium is an adventure, because when you press the button to start class, who knows, there could be a light switch in Germany that flips on and off. It seems like there's always some technical strangeness that happens. You press that button and something weird's going to happen. It's an example of a time varying system. The output of the system, every day you go to class and press the button, might be a different output. If it were a time invariant system, no matter when I went to class and pressed the start lecture button, you would always get the same result. That's an example. It gives you this idea of what it means to be time invariant. So how do we test for that property? That's a property a system has. It is either time invariant or it is not. And so we have to find a way to identify whether a system is time invariant. And so the way that we write down this property mathematically is that we say that, you know, if we have x of n as an input to this system, which is t, we get y of n. Then we go ahead and we're going to take x of n and we're going to delay it. We're going to delay it by n naught. So we're going to delay it in time by some amount. May wait until tomorrow and I'll try inputting the same signal to this system. Well, if it is time invariant, well, what I should observe is the same output that I previously observed, also shifted in time, also delayed by n naught. So this mathematical equation, albeit seemingly meaningless, actually enforces a rationale. There's a concept here, that the output that you get for an input isn't going to change when the sample index or the time value of the input is different. That's the idea of time invariance. written down as a mathematical equation. So here we have this like squared system, and we're going to test time invariance. And so the way that you test time invariance is you go ahead and you input the signal without shifting it in time, and you get an output. In this case, we input x of n, and we get this output y of n with no shift in time. Then we go ahead and we say, okay, what if we shifted the signal in time, x of n minus n naught? We put that in. But when we put that in, we get this. And then you ask yourself, so this is the output, and then you ask yourself, is this output equivalent to this output shifted? And in fact, yes, it is. This output is shifted by n naught, and this is just at n. So this is in fact this squaring function is a time invariant operation. If you put the same signal in at a later time, it will square it. Let's see. Now this is asking the question of whether or not the time compression or expansion for this is presumably for m that does not equal 1, right? Because if it's m equal to 1, it is time invariant, because that's exactly part of we get this up here, which is actually the definition. When m is not equal to 1, or for a general value of m, we get this as the relationship for a signal that's not delayed. Now when we delay a signal, we have x of m n times m times this quantity n minus n naught. Alright? And so this actually has m multiplying both n and n naught. And so that means that we're having a compression on both. It's actually occurring at a different time. It's occurring at m n naught, and not just n naught. So that means that it's shifted in time as well. So what does that mean about the time compression or time expansion? Well, it's not time invariant, and you can kind of guess that that might be the case because it's actually changing the time axis. It's either stretching it out if it's expansion or shortening it. So because the time axis is changing, but is being changed by the system, it's not going to exhibit a time invariant behavior. Any questions on any of this stuff?
Yeah, Dr. Willis, this might be a stupid question, but what if m is equal to 0 then?
What if m is equal to what?
0.
Well, then you just don't have a system. That means that y, well, you still have a system, but it's just y of n is equal to x of 0.
I see.
And so in that case, there's not a lot. This is not time invariant. Well, I guess it is time invariant because the system output never changes.
I see.
It doesn't. It's truly invariant to the. It's not really even the output being just a function of one value of the input, right? So it kind of returns into a degenerate system. Does that make sense?
Yeah, that makes sense. Thank you.
All right, so here's a conceptual diagram of how LTI works, or I mean time invariance works. So we're taking x of n, and we're putting it directly into the system, and we get y1 of n. When we get that output, we delay the output by n naught. All right, so we delay it in time, and then we get y of n minus n naught. All right, that's our first output, y1. Now we have a second branch for x to follow. In this case, we delay the input by n naught samples, and we get x of n minus n naught. Then we input that to the system, and we get another output y2. Now the system is time invariant if y1 of n minus n naught, the signal that we get at the top branch, is equal to y2 of n, the signal we get at the bottom branch. That is how we test time invariance. So applying that to say this system here, we put x into the top, x of n goes in, and what we're going to do is the system actually does this squaring of the value of n, and so x of n goes in, we apply the system, so that gives us x1 of n squared. Then we delay by n naught, and we get x1 of n squared minus n naught. So this y1 of n minus n naught, this corresponds to the top branch. That's this output here. Oh, we're a little bit after, so let me just finish this up. y2, this is the bottom branch. So we delay x by n naught. That means that x has n minus n naught in its argument. Then we apply the system, and this gets squared. So then we have y1, which is this, and y2, which is this. And we see that n minus n naught squared is in the argument here. And we have n squared minus n naught here. So these are not equal. So not TI. Alright, so we're going to leave off on this slide here. I would like you folks to go over the notes here, which is just another example. In this particular case, this is just a constant delay, and this will be a time invariant system, so it's yes. But we'll leave off there and pick up on these slides in class on Thursday, 2 days from now. If you have any questions, stay after class. You're welcome to ask those questions, but I'm going to adjourn the lecture now, and look out for homework 2 to be assigned, and the expectation is to have that quiz this time next week in class. Okay, class is adjourned. So if anyone has any questions, you're welcome to ask those questions.
Yeah, Dr. Willis, I have a couple of questions. Actually, I had some questions with the homework. For the homework.
So, why don't you, if it's sort of questions about homework and stuff, it seems like that's really a better thing for office hours.
Right.
Than for here, but office hours are thankfully held right after class, so I suggest you come to office hours for that. Okay.
Mm-hmm.
Which is just
right. I'll see you in the office hours then.
So I'll be in Zoom 10 minutes from now
to
field
Sounds
those
good.
questions. Okay. Any other
All right.
questions?
See you.
Yeah, I see you. All right, then I'll be closing the lecture. Let's see. Let's make sure to stop the recording first.